previously Bosco John. He has interest in artificial intelligence, memory, large-scale neural networks, and data analysis, and he's been working with Amazon AI, where he was an intern over the spring. He's here to talk about.
Okay. Hi. Am I working? Help me first. Okay. Does it work? Okay. So I anticipate that I'm going to speak about a topic that might be correlated with the future talk by Professor McClelland. And if there are inconsistent things, I'm wrong. Please assume directly that. So the idea is that I have the unfortunate responsibility of having to explain what I call neural networks, which are not real neural networks or models of real neural networks, but are artificial neural networks, or what is called now deep learning, and more specifically convolutional neural network, which are neural network applied to images. Then I will introduce this algorithm we've been working during last year, which is called active long-term memory, which is like more than vaguely inspired from complementary learning systems theory. And this algorithm, I will show that is able to learn different tasks sequentially, which is a typical problem in neural networks. And then I will show a recent proposal over which we also learn a generative process of the data, which we will use as a replay mechanism to maintain memory in our method. The idea is that there is going to be, over the whole talk, some soft analogy between neural networks, deep neural networks, and the brain. I will be speaking about neural networks. I will never be speaking about the brain. I hope that I can be persuasive enough that you get confused and this can mix with all your prior knowledge on real brains instead of fake neural networks. And one of the goals would be to be able to have neural networks that are able to exhibit much more sophisticated behaviors. Therefore, when we then use neural network as predictive model of the brain, we have predictive model that work in dynamic environments and over multiple settings. So what is a deep convolutional neural network? For image classification in the case, deep means that there are filters that are applied sequentially through multiple layers. So the input so in this case an image gets inside the neural network. A first module, a block, will analyze the input and give an output, and the following blocks will analyze this. As we were saying earlier, this is similar to the intuition behind the working of the ventral stream in real brains. The idea here is that convolutional, so deep, why deep? Because differently from 20 years ago, we are able now to train neural networks with up to thousands of layers. So we do not have only neural networks which with 1 or 2 layers of processing, but we can pretty much construct an infinite number of layers. So the depth of the network becomes an hyperparameter, and the depth of the network that increases parameters counterintuitively to typical statistical learning theory does not introduce overfitting most of the time. So it's an interesting property of this network. Convolutional because the same local filter is applied at every location of the image. So we are going to take an input which is going to be a big matrix. We're going to analyze it locally in a progressive stage, and at the end of this stage we are going to aggregate the information, generate an embedding vector, and use this embedding vector to make the decision of what is the content of the image. And so the classification, so this embedding vector is going to be used as an input to a logistic regression, so some almost linear model that is going to classify between however classes we are interested. We're training this through supervised learning. Most of the theory that I'll try to show will handle for reinforcement learning or unsupervised learning, because I will be only speaking about optimization, and those can be seen as optimization cases. So why memory? Why is it relevant for neural network? Is it something trivial or not? No. Neural network have a problem called catastrophic forgetting or catastrophic interference, where since learning in a neural network is equivalent to the minimization of a function with respect to some parameters. Once you have to face a sequence of functions, this means that you will face, first, you will start from some initial weights W0. You will learn to minimize function number 1, so say, which is equivalent to finding the optimal behavior in, say, your home environment. This will give you some weights, some connections that let the neural network express the function that optimally implements behavior in this environment. Now, when you move in a new environment, the function that you will require to perform in this, to behave optimally in this environment is going to be different. And this is going to require you, it's going to generate some errors, and it's going to trigger some plasticity. So whatever is, so this plasticity that gets...
Have your attention, please. We will have a technical seminar today at 12 noon today in the auditorium. Today's topic is recent advances in non-invasive modulation of memory formation and consolidation insights from DARPA, RAM, and RAM replay programs, presented by Praveen Pillai of ISSL. Refreshments will be provided. Thank you.
And if you arrive early, you will see me hand waving as well. So, because I will end up eating that talk as a revenge. But the idea is that once you change environment, you will have errors. Errors will trigger plasticity, so learning will make you find a new set of parameters. There is absolutely no guarantees that this new set of parameters will allow the network to represent anything similar to the function that was previously learned. Once you move to another environment, this is also going to be true for this. So training a neural network with gradient descent, so simply optimizing the statistics of the environment, whether this is done with unsupervised learning, so Ambient learning, whatever, SPTD, or any other algorithm where the weight change is a function of the statistics of the environment, not of all the environments that have been visited by the agent, by the most recent environment, is going to trigger this problem. And it's almost impossible because of the dimensionality that this change, this distortion, is not going to hurt the neural network because of the non-convexity of the neural networks. So this problem has been solved from the computational perspective for artificial neural network by, instead of searching 3 different sets of parameters, one after each other, by simultaneously looking for a set of parameters that satisfies, that induce optimal behavior for the network in every situation. This can happen because this neural network can have multiple configurations that express the same function because they're over-parameterized. If before there were 200 to 50,000 parameters and were many, the neural network will have 34 million parameters, and we're using a really small data set. If we were applying it to real-size images, those are going to be, would be on the order of 100 millions of parameters. And these are all optimized. So these are all target of our optimization process. So multitask learning, instead of minimizing only one task, minimize the sum of the task. And this can be done if the tasks are all in the same environment, so you get simultaneous feedback, or by random alternation of the environment. So you generate a new macro environment, which is an homogeneous sampling of all the previous environment. This is called multitask learning, and it is used in any model. Like Google Translate works now by learning to translate multiple languages so that the same neural network is able to translate, say, between Chinese, French, and English. And this is able to induce a lot of second-order effect where constraints between languages are embedded in the model. So how could the brain implement something like this? Really famous paper, I guess we'll hear more about later. There are a lot of interesting ideas inside, some human experiments, and neural networks doing the same thing. I recommend everybody to read it if you don't know it, and cite it because it doesn't have enough citation. It's like one of the most cited papers I found recently, so it's great. So the idea is, while trying to solve this problem, we came out reading the paper. Let's come up with some simplification of the theory for neural networks. So complementary learning system theory, the idea is that the brain, if there can't be a single learning system, because the single learning system won't be able to exhibit memory if learning depends on the statistics of the environment as we described. Since everybody in neuroscience can accept this dogma, then it means that there must be more than one learning system. So minimum number is at least 2. So the idea is that there is an active learning phase, which is the phase toward which during the day you accumulate new information, right? So during the day, your cortex will give you some predictions. This prediction sometimes won't be correct, this will trigger a desire for the brain to update itself, minimize the error. But this update cannot be applied globally without forgetting things before. So the idea is that there is an active phase where what has to be learned from the environment is learned on a different set of parameters or through some other mechanism without compromising the previously stored knowledge. And then there is a consolidation phase where the cortex is updated in a virtual environment through replay, sleep, or we will hear during the day much more on this. And in this virtual environment, the brain is able to generate the statistics for the cortex to update itself in a way that doesn't compromise the knowledge that is done. This could be done in a lot of different ways. I will not be speaking about memory consolidation. I will actually do a mathematical trick to avoid it. And the idea would be to have super short active and memory consolidation phase without having whole day of experience and then night, but keep at every new information, apply a consolidation step. So this was a rejected paper NIPS last year with Laurent and Lake Bosco. The other paper came out 1 month after we uploaded it online on the archive, which does exactly the same algorithm without any neuroscientific or mathematical justification. They just show that it works. But they have actually great experiments, so better than mine, to be honest. So what is the idea? There are two parallel network streams. We will call it Cortex and hippocampus. And if there is someone of you that has some actual idea about what the hippocampus or the cortex are, don't hate me. The idea is that the network we call Cortex is going to store knowledge, and it has no learning rate. So it is only able, do you want to interrupt me if I'm saying wrong things, or if you want some clarification. So the Cortex network has no learning rate during the active phase. So its only role is to generate labels, so to give supervision to the other network, hippocampus, which instead will be getting supervision from the environment. So any error that happens in the environment is going to be back-propagated in the hippocampus. And Cortex is going to help. So this is the mathematical escamotage. I'm not claiming any neuroscience in here. So the idea is that we can reframe sequential learning as multitask learning between the current environment and the past environments that have been visited. If the cortex is optimal for the past environment, it means that it can give the optimal behavior given any input from the old environment. So it's able to give supervision to this other system we call hippocampus here to simultaneously learn both from the empirical distribution of the environment and the past empirical distribution of the environment, of the previous environments. After learning, so after the hippocampus has been trained by this simultaneous environment and memory replay data sets, then basically we have an hippocampus that has all the information that were previously stored in the cortex and has the new information that has learned from the environment. The trick here is that just one sentence. The trick here is that we switch the weights between cortex and hippocampus at the end of training, so that when we move to a new task, now our old hippocampus is going to become the cortex, and our new hippocampus is going to be a fresh copy of this cortex where we are free to backpropagate. So please.
Can you describe what it means to store knowledge with zero learning rate?
So it means that this network has already been trained, right? So if you give some inputs, it will give some outputs that are not garbage. These are conditional probabilities that have been learned from the previous environment. So it's able to exhibit, to output knowledge, but it's not able to learn any new information. So the flow of new input data inside the neural networks are not going to modify the parameters of the neural network. This is the only thing that I'm saying, such that we always have an estimate of what was the knowledge at the previous time step. And we will use this estimate to compute an error that says how much we are forgetting. And we're going to minimize this error together with the classification loss of the new environment. Somehow. So knowledge, I mean function. So function, here I'm interested in a relationship between an input and an output, pretty much. Here is a really simple setting, so I'm just saying image, what is the content of the image. But it might be a reinforcement learning environment, a maze, and an optimal policy to explore the maze. This is going to be represented by a function. This function is parameterized by a neural network. So I'm interested in the knowledge in the function, which I do not want to force, which is a constraint that does not exist because of non-convexity of the neural network, to say that the function stored in the neural network is the same thing as the weights of the neural network. The trick is that there are going to be multiple functions that the same function can be explained by multiple configuration of the neural network, and small perturbation of weights of a neural network can drastically change the output function. So this comes out of the strange error landscape of neural network given by the recursive application of multiple functions. So so the idea is that the active long-term memory algorithm is something really simple where we have a network that was previously trained. So there will be this Cortex, which has a function in it, so some parameters. We initialize the other network, H, from these weights. So now at time 0, when we start this new task, H and C gives exactly the same prediction. So if they receive the same input, there is no mismatch between their outputs. Then we start giving input of the new distribution to the hippocampus. And the feedbacks generated by these inputs are going to change the H function with respect to C. This is going to generate an error in their output. And this error is going to generate another feedback, another gradient that our network is going to try to minimize. So the idea is that there will be an active step where the hippocampus is updated from the real data, and the memory step where the hippocampus and the cortex are both forwarded the same data from the old distribution. A mismatch is computed between the two outputs, which is an estimate of how much forgetting is happening, and the weights are changed in a way to reduce the amount of forgetting. After this happens, after we converge for the new task, we can switch the weights from H to C and then start again for a new task. The truth is that I will always show this one task transfer kind of experiment because they're difficult enough like this. And for learning, we will keep alternating active step, memory step, till the convergence of the network. So the idea, again, in a more graphical sense, there is an active step where the inputs get inside the neural network H. This gives an output that gets inside an error function. The red arrows are like the error, the update of the error that is backpropagated and update the parameters. During the memory step, same input both through H and C. Now, there are no real labels. Both network output give an output. C output is going to be considered the label for network H, and then a loss function between those two outputs. So the cross entropy between the probability distribution predicted by H and the probability by C is backpropagated back to H. So this is a multitask learning problem between one task is learning the new task, and one task is not forgetting the old task. So this again, H receives the input, H receives label, error, backprop during the active step. And now instead, H and C, same input, compare the outputs, backprop. Now, this requires, as you can see here, sampling from the old distribution of data. Because in order to have an unbiased estimate of the function generated by C, we need to use the same support input of the inputs that we used for training it. So this is a bit. So C was like previously trained. OK, so the idea is actually, I will show you some experiment that will be done like this. I train C on dataset A. Then I train H on dataset B. And then I test again H at the end of the training on dataset A. So I learn one task, transfer to another task, and then test back my ability to predict on the first task that I learned. This is going to be the evaluation for the experiment that I'm going to present like in 2 slides. And so there will be 2 differences, and then a third type of replay mechanism. The simpler replay mechanism is to store all the data from the previous distribution in some magic mechanism. In a computer, we just need a big hard drive, and then resample uniformly from this. This resampling allows us an unbiased estimate of this function that under the case where C is actually an optimal function for the previous dataset, this is exactly mathematically equivalent to multitask learning. So there are 20 years of machine learning research demonstrating empirically that it works.
So essentially, the memory that you have approximates the distribution of all the data that you have seen already.
the conditional distribution of the outputs given the data. Okay, so C is a conditional distribution. And then exactly what I will, the rhetoric of the whole talk is like going through mechanism, going from sampling, so estimating the empirical distribution by resampling, to learning the empirical distribution itself, so what we could call a generative replay mechanism, and use this one for the memory. So we have a data set is a joint probability, x and y. The neural network is learning p of y given x. So if we sample from p of x, we can use the joint probability to extract the marginal of both things, right? Yeah. Yes. So, and it works really well. And I discovered it while driving here. So the naive approach is instead to use the data from the current task as inputs for this loss. And if the two tasks are defined over the same environment, so say one time is recognizing who are the person, the name of the, telling the name of the persons in this room, and in the other case, the task is predicting how much do they earn every month, then these tasks are based on the same input distribution. So I can resample, I can learn one task, then start learning the other task and use the same input distribution to generate my loss. If, say, this task was between you guys and USC students, which come from two totally different distributions, except like 3 or 4 of us, right? We are gonna need to using the wrong data set is gonna give a biased estimate of this loss function. So there is some latent notion of how similar the input data set need to be in order for this naive approximation to work as well as sampling real data. So first data set, highly controlled data set, which I think might be related to the project you were saying before. So this is a data set collected by Laurent Titi in the iLab, in our lab. So it's called iLab. So there are 20 million images, around 1,700 different, I actually think it's 174. There are 174 different objects, 1,300 images for every object. So this is a super controlled data set where for every object we have multiple viewpoints, multiple camera options. And these objects are all really simple vehicles. These are like matchbox cars that have been bought on Amazon. And then the picture can either come from A and B, and we will use A, which is an arena that rotates. So we have a turntable, multiple cameras. So we will have, for the same object, 88 viewpoints generated by rotating the turntable or changing the camera angle. So we are going to use a subset, only 850 images, 10 categories to classify, and 88 viewpoints. So dataset task 1 has, given these images, predict what is the category and what is the viewpoint. Dataset 2 is Cypher10, which is a classical neural network baseline dataset, which has 50,000 images, so drastically smaller number of images, 5,000 images per category, 10 categories, but these categories goes from airplane to deer, cats, and humans, and boats. So a lot of variety with respect to the previous dataset in the semantic of the image, but no every image has only one picture. So we have no variety in graphical factors. Actually, there are a lot of bias. Pretty much there are only pictures from the front, since humans don't take pictures of their cat from the back or whatever. So experiment is like sequential training between iLab and Cypher10. So the idea is to demonstrate that it's possible to learn multiple tasks if the supervision is asynchronous, and we can avoid the catastrophic forgetting through the addition of this memory step together with a normal gradient descent step. So, as I said before, train Cortex on dataset A, train hippocampus, then initiate in hippocampus from Cortex, train it on dataset B doing the memory step, consolidate, so switch back hippocampus to Cortex, and test Cortex on dataset A again. So this is our evaluation. The training of Cortex, on the value on the top, the accuracy at the top is going to be our upper bound. So if you're able to fully remember things, we're going to have exactly the same number. Otherwise, it's going to decrease. How much error, so how much forgetting measured as the difference in the performance before and after training on the other data set is going to be our evaluation measure. So the idea is that we have two configurations. So first train iLab, then Cypher10. And these are the results, first training on iLab, and then training on CIFAR10. So what I'm showing is the accuracy on the final data set. So in purple, there is going to be the accuracy after. So 0.78 is the accuracy in categorization after training on CIFAR10. 0.75 is the accuracy in viewpoint. And 90% is the accuracy achieved on CIFAR10. Before training, the accuracy was at 84 and 92% instead of 78 and 75%. So in this situation, we use is the naive condition. So we use the current task inputs to generate the memories, to generate the memory step. In the opposite setting, instead, when we use the real images, so we can sample from the ground truth distribution, we get 83% and 92%, which is like exact memory, no forgetting at all from the previous task, and we get only 3% loss for the CIFAR10. Notice that these results require some hidden work that if people are actually working with this model, they have something called batch normalization in it, which means that parameters of the neural network explicitly use moments of the data distribution. And these are going to generate even bigger memory problems because the distribution of the statistics of the environment is an explicit parameter of the neural network, not only implicitly collected by the learning rules. So what is the limitation here? Sorry if I'm rushing, but I would like to show the GaN results. So the limitation is that we require sampling of data. And how could a brain, if like an image is like a pattern of activity on our retina or LGN, when we think of an image in terms of a collection of pixels, how could the brain store millions of patterns of activation of LGN in a way similar to what we do in a computer, which is take the activation and stack a memory bank, 1, 1, 1. We would need like a lot of LGNs to stack a lot of LGN activation. So the idea is that trying to, instead of storing the data, learning a model that can hallucinate the data so that we are able to sample from the data through an implicit probabilistic model. And a recent improvement in machine learning called generative adversarial networks come to help. So these are methods to learn arbitrary distribution through a neural network procedure. So it's a method that the problem of learning, unsupervised learning of learning distribution is problematic because it requires a specification, a formula to write down the distribution that you're interested in learning, right? So typically say, we assume the data are normal, we minimize the parameter of the likelihood of a normal distribution. But for images which have a lot of correlation between pixels, it's almost impossible, and people have been trying to define likelihood function for natural images since the last 20 years. Aaron Simoncelli, one of those that was cited in one of the previous papers. And the idea with the GaN is that we are both learning this likelihood function, what is the probability distribution, and what are the parameters of the probability distribution together. How does a GaN work? Generative adversarial network, or GaN. It works by having two computing networks, a generator, which takes noise as input and gives output images. At the beginning, these images are going to be complete trash, just random pixels. And then another network that takes these random images as input, take real images as input, and compare them, and learns to classify between the two distributions. This is a simultaneous optimization problem, so it's a game. And in terms of game theory, there exists a solution, a Nash equilibrium, where the discriminator is optimally good at discriminating between fake and real data, and the generator is able to fool it, implying that the data generated by the generator corresponds to the real data distribution. So this is a generative adversarial network. This is the basic mechanism. So how good are images generated by a generative adversarial network? The truth is that if I didn't show this slide and made this joke other 15 times, it would be quite difficult to distinguish between the two. But the truth is that there is some perfect white that my neural network is never able to learn. And I kind of normalize. The pictures are dark by itself, but real images are on the right. And you can distinguish it only because the white of my neural network is really bad. These are full of artifacts. But like, these networks are highly unstable. So the one on the left looks almost satisfying. If you look at it from far apart, the images are tiny, so it's difficult to create details. But the epoch after it, it looked like it converged. But then the epoch after it, this is what happens. So this is one epoch after, that's 5 epoch after. These are phenomena called the mode collapse, where the two networks derail to some strange equilibriums and stop generating meaningful distribution. So this is why everything is pretty early results here, because I do not have an automatic way to stop my generator and say you are good. If I keep training my generator after it's learned, the generator will diverge. So the results that I'm going to show in the next experiment depends on me hand-picking pretty much the last epoch before this transition. So third data set, Cypher 100, exactly the same size of Cypher 10, but it has 10 times more categories, which means 10 times less images for each category. Train on Cypher 10, test on Cypher 1, first pre-train Cortex on Cypher 10, then train on Cypher 100, and then go back to Cypher 10. Now, see exactly the same experiment as before, but we are not only using the real images and the naive replay, one slide, and the naive replay, but we're also going to be using the GaN generated images. So pretty much this is what happened, exactly the same, only that during training of the Cortex on Cypher 10, we train also GaN, and during training of the hippocampus, we also replay images from the GaN instead of sampling from the real distribution. And what happens, you can see like the real condition, the naive, and the GaN condition. In blue, we have the results on Cypher 10 before. In red, we have the results post-learning. And in orange are the results on Cypher 100. So as you can see, there is a big loss for naive. These are the real data. So this is how the algorithm works using the true empirical distribution. And this is using the approximation of the empirical distribution, which is like 0.1% worse than this. And just to finish, now I'll just go through the drawing and persuade you that are complicated. Now, since we have to both learn a classifier, a P of y given x and a P of x now, this P of x will have exactly the same problem, the same catastrophic forgetting problem. So there can be an active long-term memory procedure, so active step and memory step, also for the GaN. This is the active step, which is exactly what we explained before. This is the memory step. Basically now we have two generators. And these two generators, one that approximates all the previous distribution, and one that is learning the new distribution. And we just need to oblige the newer generation to be able to generate images from the older distribution. We don't need any empirical supervision for this because we can already sample from that distribution. And this is it. So it only complicates a bit the story. I don't have experiment for that, but there is another paper that came out last month. This time accepted for NIPS from SKT. The group is particularly interesting, a new Korean group. They demonstrate exactly the LTM algorithm with some flows in it, but they use it on really simple images, like this number generation, not real images generation. So I tried those experiments of before in this setting, and right now we're still crashing. So pretty much this is it, some boring things. And that's like a unicorn, maybe a cat, maybe something that neural network generator. And those are the people, National Science Foundation, Office of Naval Research for the data, Intel Corporation, which is currently funding a grant on this, and Amazon that has been funding my private computing for the last year. Okay, so that's it.
Sorry, we've lost time for questions now, but we'll have a lunch break in a minute. Introduce the next speaker.
Please help yourself to refreshments quickly.